Hello, everyone. Hi, good morning. And nice to see you all here to listen to Xu Qing's presentation about his research project. So first of all, for those of most of you, I believe, know me, and for those of you who don't, my name is Wenting Duan, and I'm the senior lecturer in computer vision. So Xu Qing did the Euros project with me in his second year summer, and he was awarded with the Euros award from the university with £1,000 to carry out this research, and then followed by the good research he conducted during the summer, he was able to continue with similar projects, and then being able to actually publish a paper at the end of his project, and it was accepted in a very good conference called the Nuclei conference, and in its associate workshop. His project is about cell segmentation. So I will pass on to Qing to discuss his research. And at the end of the session, you will have a chance to also ask me and him any questions you have. Okay, over to you, Qing.
Okay. Okay, so first I would like to thank Wenting and Kieran for giving me this chance to share our work and what we did in this summer. And the main problem we solved is actually is cell segmentation. And here is what I'm going to talk about today. And so we will start from the introduction. And in traditional medical diagnosis, microscopy images are manually analyzed by medical professionals. However, this way is time-consuming and subjective because the result of diagnosis usually depends on the experience of experts. So currently, people hope this task can be completed by computer. And in this case, nuclei segmentation plays a very important role in this task. And also, I would like to share why we want to do this project. And actually, we did another project related to tumor detection in Euros 2020. And I have to say it was an amazing experience, and also it's my first time to learn deep learning. And in this project, everything starts from scratch, and we need to create our own dataset first. So we and from the prepared images, we manually extract cell samples and label them. And then this dataset is used to train a deep learning model. And finally, we combine the model with sliding window algorithm to detect and classify each cell in images. This project also got the Euros 2020 award. And if you are interested in this project and want to get more details, we have provided a poster link here, and you can check it later. And if you want to try doing this project by yourself, like training your own model, and we also provide a GitHub link here, so you can download our code and train it. And so we completed the cell segmentation, but it just provides the location for each cell and the defined bounding box usually includes other useless informations. And to provide a more precise result, we decided to do cell segmentation, which is a pixel level task. And usually we will meet some challenges when doing the cell segmentation. The first one is illumination. So if you see in these 4 pictures, you will find some cells are bright, which is easy to find them, and others are not very clear, which is difficult to be detected by people and also for computers. And secondly, a microscopy image often includes multiple cells with irregular shapes and different size. And the final one is overlapping. Actually, this is a main problem for instance segmentation. And you can see in these images, some cells are connected to others, which is hard to segment out each one. And so to solve this problem, we also have some traditional methods such as Osteo and Fuzzy. These methods are easy to implement by using Python, C++, or other languages, but not very efficient. And we provide some examples for these 2 methods, and in the right side we can see these methods can roughly extract cells from images, but will lose some information about cells. In addition, deep learning networks have made a great breakthrough in image classification and segmentation. In terms of medical image segmentation, a very popular network is UNet, which is proposed in 2015. And it's easy to construct and train and performs better than traditional methods. However, it still has limited performance for complex images because of its simple convolutional layers. So in this case, the aim our project is to further improve the performance of UNet in cell segmentation. And then we also want to save the time spent in evaluation of medical images and reduce interferences from human factors. So next, I will introduce our methods. First, we construct a new multi-scale split attention block. This block includes 2 components. One is split attention operation, which can extract and fuse multi-scale features from input images. Another one is multi-scale kernel size. Kernel size. Here we add convolutions with different size, which can make the network get a larger receptive field. And in the next step, the built block is used to replace original convolutional layers in UNet. And also, we keep some useful architectures of UNet, such as skip connection. And finally, we add a sigmoid function at the end of the network to complete binary segmentation. So this new network is called the MSA UNet. And for the loss function, we combined the advantages of dice loss and the focal loss which is able to improve model performance. The weight of these two loss function is optimized by F1 score and IOU. And we use 5 metrics to evaluate our models quantitatively, where precision, recall accuracy, and F1 score are based on confusion metrics, which shows the performance of detecting nuclei. And the IOU indicates the similarity between the predicted segmentation mask and its ground truth label. Okay, so let's move to our experiment. First, the data we used to train model is a public dataset from Kaggle. It includes 670 nuclei images and their ground truth labels. And we randomly select 600 nuclei images as the training set, and the remaining 70 samples are used to test our models. In addition, to avoid overfitting in the training stage, we apply some image augmentation methods in the datasets, such as randomly horizontal flip and vertical flip. So here is the training stage. Here is the training strategy we used in the experiment, and we provide some hyperparameters we set in our experiment. And besides using combined loss to train our models, we also select a traditional loss function cross entropy to train our models for computation. And we also select 85% of the training set as okay. So we also selected 85% of the training set in the training set, and the remaining 15% samples samples are used to validate our models. And to compare MSA-UNet with other popular models, we also train UNet plus, and double UNet models. And here in the right side, we provide the results of the training and validation on MSA-UNet. And and you can see the result shows the model trained by combined loss function got the higher IOU score than trained by cross entropy loss function. So here here is the result of our experiment, and we evaluate all models on text data set by using our defined matrix before. And so you can see MSA-UNet got the highest score in the most of metrics, and also in the right, also in the right side, we visualize some of the segmentation results. So you will find the MSA unit can solve some of the complex images, such as cells with different shapes, size, or in different illumination environment. So finally, in this project, we propose MSA unit for nuclei segmentation, and the proposed module shows higher performance than UNIT and other popular models. And in the future study, we will focus on instance segmentation and test MSA unit on different data sets, not only just for nuclei images, but also for different kinds of medical images, such as MRI or CT images. Okay, so any questions here? So if you have any questions, please just
yeah, thank you, Qing. Yeah, we are happy to take any questions you have regarding to this research or regarding to the the project we carried out with either EUROS or the final year project.
Okay. So if you are interested in this project, we also provide the paper link here, so you can check it and get more details about the network construct and other information. And if you want to try train and test your own models, we also provide the code link and dataset link here, so you can download them and train in beautiful model. But you need to have a high performance computer first, so you can just follow up some of the requirements in the code in the GitHub link.
Yeah, they can use Google Colab as well, isn't it? Google Colab provides some probably free usage of GPU, so they could train on Google Colab potentially. Yeah.
Yes. Okay. It just needs a graphic card with 6 GB memory, I think. So it's not too. It's I think most of the students can train it, maybe, because I think it's not very high requirements.
Yeah. Okay, so if there is no question, thank you very much. We are sorry about today. Qing couldn't really turn on his webcam due to signal problem because he's joining from China. So thank you very much, Qing, and see you soon, hopefully.
Yeah.
Thank you for listening.
Thank you for listening.